Hello friends, welcome to the channel Sky's the Limit. In this video we are going to discuss the concept of magnetism and matter, which is the physics concept as per the syllabus of hstr and gpstr. So before going to magnetism and matter, let us understand what are magnets, what were magnetites, and what was magnetism. So, see, it was known to the people as early as 600 BC that a kind of iron ore was found in a place called Magnesia, which was located in Greece. What they do, what happened there were it was attracting the small bits of iron. The ore was named as magnetite. This phenomena of attraction of small bits of iron towards the ore was called magnetism. The iron ore showing this property was called magnets. Okay, the magnetite which was found was irregular in shape and they were having weak magnetism. Okay, it was found that the piece of magnetite when it was suspended freely, it always roughly points in the direction of north south direction. Okay, north south pole of the earth. So this natural phenomena has attractive and directive properties at the same time. Based on this property, magnetic needles were used in the navigations of ships. Then it was also nowadays in the modern gadgets, it is used in audio cassette, headphones, ATMs and credit cards, etc. Because since it was used in the navigation of ships, magnetite is also named as lodestone, which means the leading stone. Okay, this can be asked what is called as lodestone. You can say the magnetites were called as lodestone. Why? Because they were leading the people, okay, during the navigation. Then this natural magnets were weak and they were having irregular shapes. So therefore, since they were weak and irregular, there was a need for the introduction of artificial magnets. So artificial magnets were made with the mixture of some amount of magnetite and some pieces of iron and steel. These have the desired shape and strength. Some of the artificial magnets in use are bar magnets, horseshoe magnets, and then we have compass needle, magnetic needle, etc. Magnets and magnetic materials are used in the modern day, as I have told. It is used in audio cassettes. Bar magnet is one of the form of artificial magnet. So it is one of the example of artificial magnet. Bar magnet can be of the shape of cylinder, or it can be it can be shape of rectangle, or it can be in the shape of cylinder. It will have two poles in it, that is north and south poles. Whenever the magnetic needles were suspended freely, it was observed that the magnetic needle always pointed towards, this is north and this is south of the magnetic needle. The magnetic needle north south points always pointed towards the geographic north and the geographic south of the earth. It always pointed towards the geographic north and geographic south of the earth. So these poles were given north and south name. Now here this poles were given certain amount of strength. Okay, the positive, that is the north pole, was having the pole strength of qm, that is plus qm, and the south was having strength of minus qm. This is similar to the charges of electric charges, as if there are positive and negative charge. Positive charge will have plus q charge and the minus q charge will have, sorry, the negative charge will have the minus q charge. So similarly here the north and the south poles were having the pole strength, that is plus qm and the minus qm. So this bar magnet, this north and this was south, this north and south, that is the two poles were separated by a distance of 12. Whenever the two poles is separated by a distance of 12, then there exists the magnetic moment. Okay, so magnetic moment, this is plus qm and this is minus qm. So what is the definition of magnetic moment? Magnetic moment says that it is the product of either of the charge into the distance between the north and the south pole. This is your expression for magnetic moment. Now, there is another property, very important property of bar magnet, is that the magnet, in magnet, there don't exist the monopoles. So we can say the monopoles do not exist. What does it mean? Listen very carefully. Monopole does not exist. It means that whenever you break the magnet into two pieces, you will get this type. This is north pole, this was south pole. When you break, there will be generation of south pole over here and the north pole at this point. So whenever you break the magnet into large amount of pieces, there will always be two poles to it. Okay, no matter how small is the size of the piece, but still it will have what? Two poles. So we can say monopole, that is single pole, do not exist. Always there will be dipole. Okay, there exist always dipole. Hope you have understood what is bar magnet and what are the basic properties of bar magnet. We have very important concept, that is magnetic field lines. So there are certain properties to magnetic field lines. So as we have studied about bar magnet. So similarly here, suppose you have bar magnet. Whenever the then we have magnetic field lines. So before going to the property of magnetic field lines, you need to understand this, that suppose you have a bar magnet and the iron fillings is sprinkled around it. You can notice from the experiment, it was noticed that it followed a particular pattern. Okay, the iron fillings were arranged in the particular pattern, and some of the iron fillings which was far away from the magnet was undisturbed. Okay, they were not forming any pattern. So then it was concluded that there is some imaginary boundaries around the magnet which is known as magnetic field lines, and that magnetic field line is not up to the infinite. Okay, it is not up to the infinity, it is up to certain level. So there is a imaginary boundary. Okay, so where the magnets can attract the iron fillings towards it. So now this pattern was observed, and it was observed that the patterns, this north and the south, the magnetic field line started from the north pole and it went back to the north pole in this direction. So it was forming a closed loop. Now we can say outside the bar magnet, the direction of magnetic field lines is from north to south, and inside the bar magnet it is from south to north. So with this we can state the first property of magnetic field line, that the magnetic field line forms the closed loop. What it forms? It forms the closed loop. That is, it starts from north and it ends to the south, and from south it goes to the north. So it will form a closed loop. And at every point to this loop, if we draw the tangents, okay, if we draw the tangents to each and every point on this magnetic field line, it will give you the direction. What it will give? It will give you the direction. This is the second property. Okay, the tangents drawn to the magnetic field lines will give you the direction at that particular time. Then the third point is that the magnetic lines will never intersect each other, or they will never cross each other. As I've told, at every point it will give you the direction of the magnetic field. Suppose it cross, okay, if it intersect, then what happens? At this point there will be two directions. So at one point it is not possible to have two directions. Understood? This is the third property. The first one, it forms a closed loop, and the second one, the tangents to the magnetic field lines will give you the direction, and the third one, it will never cross each other. And the fourth one, if suppose you are considering a small area and number of magnetic field line passing through that area at particular instant of time is known as magnetic flux density. So whenever you want to remember certain thing, the main strategy to remember the point is this scramble. Okay, you have to scramble and you have to read it. See, with this key point, you can say the properties of magnetic field lines. That is, it forms a closed loop, it starts from north pole and then it goes to the south, and from south it will come back to the north. It forms a closed loop. Then that is direction. From direction, it should click to your mind that the tangents drawn to the magnetic field lines will give you the direction at that point. And then if you see this cross mark, you need to understand that the magnetic field lines will never cross each other. Okay, the reason is that at particular point it cannot have two directions. Okay, then the fourth one is, if suppose you are considering a small area, then the magnetic field, number of magnetic field lines passing through that area at a particular instant of time is known as magnetic flux density. Hope you have understood what is magnetic field lines. In the at the end of the video, I will be providing you with the clear notes of this magnetic field lines properties, and then the previous bar magnet, and then the upcoming I'll be teaching you the Biot-Savart's law. So you don't worry about the notes. I will be providing the complete notes for the hstr syllabus. Okay, then next we have Biot-Savart's law. We have very important law as per the syllabus of hstr, that is Biot-Savart's law. So Biot-Savart's law, it is the experimental law which deals with the magnetic field at a point due to the current element. Now when I say this current element, you need to understand that what is this current element. This is the product of current and the length segment. Okay, suppose this is the wire through which current I is flowing. If you are considering the small segment of this length, that is dl, this together is called as current element. Okay, hope you understood this. So what is Biot-Savart's law? Suppose you have a wire through which current I is flowing. You took the length element out of this small segment of length, that is dl. There is a point P at a distance of, okay, I'll take it over here. This is point P which is at a distance. This is the distance. Okay, this is point P. So what you have to find is, you have to find out what is the magnetic field dB due to the small length element dl. Okay, that is due to the current element idl. So here Biot-Savart's law states that, listen very carefully, this is very important. See, the first proportionality is the magnetic field is proportional to the current. Okay, that is, what is the current flowing through this? That is I, right? We can say it is directly proportional to the strength of the electric current I, and then it is directly proportional to the length dl of the current element. And then we have the third one, it is directly proportional to the, this is theta. Okay, it is directly proportional to the sine of the angle between the current element, that is this current element, and the line joining the point of observation. This is our point of observation, right? So line joining the point of observation with the current element. Okay, so this is third proportionality. Then the third proportionality we have, it is inversely proportional to the square of the distance, that is r. Okay, which is square of the distance r of the point from the current element. This is this distance. So from this all proportionality, we can say that dB is proportional to I, that is our current. We have dl, that is dl, then we have sine theta, and then we have square of the distance, that is r square. So therefore this is very important law, that is Biot-Savart's law. So what it says, that is dB is directly proportional to I dl sine theta by r square, and this proportionality sign is taken by dB is equals to k I dl sine theta by r square, where k is the constant. Now this experimentally it is found that the value of k is mu naught by 4 pi, and it is equal to 10 raised to minus 7. Okay, so mu naught by mu, what will be the value for mu naught? It is mu naught is equals to 4 pi into 10 raised to minus 7 Tesla meter per ampere. Okay, this is called as the absolute. Mu naught is called the absolute permittivity, okay, permeability of the free space or vacuum. Hope you understood. Now what we have, k is equals to mu naught by 4 pi. So therefore we can write dB is equal to mu naught by 4 pi. In place of k we are replacing it with mu naught by 4 pi, that is ideal sine theta by r square. Okay, this is the law of Biot-Savart's law. So this Biot-Savart's law can also be written in the form of vector. Okay, the vector notation of Biot-Savart's law is, since magnetic field is a vector, since it have direction that is from north to south, so therefore we say it is dB vector is equals to mu naught by 4 pi. Okay, mu naught by 4 pi, we have I, even this is length and this is your r divided by r cube. So this is the vector notation of Biot-Savart's law. You don't need to know the derivation of this. You just have to remember what is the vector form of Biot-Savart's law. This can be asked in the objective. What will be the vector form of Biot-Savart's law? If it comes, you can directly say that this will be the vector notation for Biot-Savart's law. So the direction of that dB, okay, this dB is perpendicular to the plane containing your dl and r. Okay, so therefore we can say when your theta is equals to 0, okay, we get what we get. See here, when your theta is equals to 0, when we say this theta is 0, that means what? There is no angle over here. It is something like this only. Okay, there is no theta, that means it should come here and it is like this. So therefore what will be the magnetic field? There won't be any magnetic field, so therefore we can say it is 0. It can be asked in the objectives. It can be asked in objective that if suppose your theta is 0, then what will be your magnetic field? Okay, what will be the magnetic field? It will be 0. There's a magnetic field at a point on the thin current carrying conductor itself is 0. On itself is 0. Hope you understood what is Biot-Savart's law. Let us recall it. So Biot-Savart's law, it is the experimental law which deals with the relationship between the magnetic field and the current element. So current element is the product of current and the length element dl. Suppose there is a point P at a distance r from the current carrying wire. Suppose I current is flowing through this wire. We consider the small segment, that is dl, and we have the theta, that is the angle formed between the current element and the line joining the point of observation and the current element. So that is theta. Then we have, this is the distance r. So therefore Biot-Savart's law states that Biot-Savart's law is directly proportional to the current, directly proportional to dl, directly proportional to sine theta, inversely proportional to the square of the distance, that is r square. So this is your Biot-Savart's law equation. So in the previous hstr question paper, this law or the directly they have given in the options, they have given various equations, and they have asked which is the correct form of Biot-Savart's law. So this is the correct option. If they ask you what is the vector notation, then you can say that this is the vector form of Biot-Savart's law. Hope you have understood Biot-Savart's law. Thank you friends. In the next upcoming videos, we will be dealing with solenoid toroid. Okay, so stay connected with me. Don't forget to subscribe to my channel and share with your friends. Hope it will be helpful for you all in your HSTR and GPSTR preparation. Thank you.